Now we want to know the effective number of particles per hexagonal unit cell. Per hexagonal unit cell, that means look, unit cell is hexagonal prism type, and if we want to know if we want to see this hexagonal unit cell from above, then we'll only see one such hexagonal places, one such hexagonal place here, one such hexagonal place here. Suppose the three-dimensional hexagonal prisms are attached to one another in a compact structure like this. Then the question is, what will be the contribution of this red spherical particle which is standing on one vertex point of such hexagonal face? There are 6 such vertex points, and we are only considering one such. Of course, you see, one such particle contributes to 3 hexagonal 3 hexagonal unit cells in this layer, but also there are 3 unit cells above this layer, like this one, the yellow. This particle, one particle alone, contributes to 6 unit cells, 1 in the 3 in the immediate layer and 3 for the above layer. So one particle alone contributes to 6 unit cell, one at a time. Since there are 12 such particles, because if we try to draw the other face of the hexagonal prism like this one, there will be 12 particles in total residing at the vertex point, 1 2 3 4 5 6, and 1 2 3 4 5 6, 12 vertex points are there. So total contribution of one particle becomes now 12 multiplied by 1/6. Vertex area is 1/6. Vertex points are 12 in number, so the effective contribution will be 12 multiplied by 1/6. Keep that in mind. Now, what about the particle residing at the just at the center of hexagonal face? There are 2 hexagonal faces, so the face center shear will be, the face center shear for one face is half. There are 2 such faces, so the contribution will be 2 multiplied by 2 hexagonal face multiplied by half. Why half? Because this particle is divided into 2 layers. One is this layer, another is the layer above. Suppose this yellow layer. Okay, so 2 hexagonal faces and face center share is half. Total contribution will be 2 multiplied by half. And what about the 3 central particles which are at the vertex points of one regular triangle? Full contribution, so there will be 3 central particles. Now the contribution will be 3 from this triangle, 2 multiplied by half from these hexagonal faces, and 1/6 multiplied by 12 from this case, the vertex particle at the faces. So overall there will be 3 plus 2 into half, that is 1, plus 1/6 into 12, that is 2, that is 3 plus 1 plus 2, that is 6. So number of particles per hexagonal unit cell thus is 6. Okay. Now what will be the packing efficiency now? Packing efficiency. We know the packing efficiency stands for number of particles multiplied by 4/3 pi r cube, because they are spherical particles, upon volume of hexagonal unit cell. Now the volume of hexagonal unit cell, calculation of this volume is a challenging task. We know the number of particles is 6 multiplied by 4/3 pi r cube, that is easy. But what about the volume? Volume is area into height, so we have to calculate separately the area of hexagonal unit cell and the base area of hexagonal unit cell, that means the area of this hexagon, and height of hexagonal unit cell. in step by step. We see first the area of hexagon. Since the hexagon is constituted by three regular triangle, we can say that area of hexagon is 6 multiplied by 6 times the area of triangle. Now what is the area of this triangle? One such pizza piece. What is the area of such pizza piece? You see here the 6 multiplied by half into base into height. As we know, the area of triangle is half into base into height. Base of triangle is this is the base. Okay, so base is base is formed by two such spheres. If radius of one such sphere is r, then the base of the triangle will be r and r plus r, that is 2r. So 2r is the base. What about the height? Calculation of height, just simple, from right angle triangle formula. If this is r and this will be 2r, because there is one particle at the center and one particle at one vertex point, and when these two particles touches each other, we see that the line becomes addition of two radii, r plus r, that is 2r. So this one, the hypotenuse, this is a right angle triangle. You see this one is the 90 degree, and that is the hypotenuse, that is the base, and this is the perpendicular. So we know the perpendicular square plus base square is equal to hypotenuse square. Here the base is r here, this is the base r, and we have to find out the height of the perpendicular, the length of the perpendicular, that is x. Suppose this one, the red line stands for x. Okay, and so this is 2r and this is r, and this one is unknown. So r square plus x square is equal to 2r square. Solving this, we get x square equal to 3r square. Why? Because this is 4r square, this is r square. 4r square minus r square is equal to 3r square. So x square is equal to 3r square. Solving, we get x is equal to root 3r. So we get the height of the perpendicular, that is root 3r. So put it here. Base is 2r, root 3r is the height. So 6 into half into 2r into root 3r, that is 6 into root 3r square. So this is the area of the hexagon. We get the area. Now what about the height of the hexagonal unit cell? This is more challenging. Height of hexagonal unit cell. So in order to calculate the prism's height, we have to see the whole picture here. This one is the hexagonal prismatic unit cell, and inside which there is a triangle here. We can divide the hexagonal unit cell from this particle here into two pyramidal structure, like this one. This particle, that particle, this 3 red particle and this blue particle form one pyramid here. You see the pyramid, this linked by this, that, and that one in the in behind the dotted structure, you see. So this is the pyramid here, and if we want to find out the height of the prism's height, the hexagonal prism's height. Height is divided into height of two pyramids, this pyramid and the inverted one here. You see 1 2 3 4, this one is also a pyramidal structure. This one is also a pyramidal structure here. Sorry, this and that, this is one pyramid, and this. So we can consider the hexagonal prism as a summation of two pyramidal height. Okay, now we see here, we extract this pyramid. Suppose here this one is the pyramidal structure, this is the blue ball here, and this is the base. These three are base. So suppose this and that touches each other.